The cameras caught it. A ball of fire, moving faster than sound, brighter than lightning, tore across the sky over South America. And then it did something that no one in the room was prepared for. This wasn't just a fireball. The way it moved, the altitude it chose to detonate at, and the specific region it targeted, all three of those things individually would raise eyebrows. Together they form a pattern that hasn't shown up in the data in decades. And right now, tonight, that pattern is not over. Here's the paradox that should stop you cold. Fireballs enter Earth's atmosphere every single day. Hundreds of them. Most burn up silently. You never hear about them. So why are the researchers who track near-Earth objects, the ones who have seen thousands of these events, why are they the ones who can't sleep right now? Because what happened over South America doesn't fit the model. And when reality stops fitting the model, that's not a data error, that's a signal. In the next 20 minutes, we're going to pull this apart layer by layer. We'll start with what the cameras actually captured and what the mainstream coverage completely missed. Then we'll go into the science of why this fireball's behavior broke the rules. Then we'll zoom out, because this event didn't happen in isolation. And by the end, you'll understand why the word spreading isn't hyperbole. It's the most precise word available. If you follow this channel, you already know we don't do panic for clicks. We do data, we do pattern recognition, we do the work the headlines skip. Hit subscribe if that's what you're here for, because this story is not finished. Let's go. Let's start with what actually happened, and I want you to notice something very specific as I describe this. On a night that felt completely ordinary across northern South America, multiple dash cameras, home security systems, and at least 2 airport surveillance feeds recorded the same thing simultaneously. A streak of light, not a quick flash, not a blink. A streak, sustained, accelerating and changing color as it descended. That color shift matters. We'll come back to it. Witnesses described a sound that arrived almost 30 seconds after the light disappeared. In the Brazilian interior, people reported windows vibrating. In parts of Bolivia and Peru, emergency lines received calls about an explosion with no visible source of fire on the ground. That last detail is critical. No ground fire, no crater, no debris field reported at the initial impact site. Now, that should immediately tell you something. Because when a space rock hits the atmosphere and survives all the way to the ground, it leaves evidence. It leaves a crater, fragments, a burn scar. This one left none of those things, which means it didn't make it to the ground. What the object did, and this is the part that's now being analyzed frame by frame, is it detonated. Mid-air, at an altitude, and with a pressure signature that immediately flagged the event in monitoring systems that most people don't know exist. When a space object undergoes what's called an airburst, a mid-atmospheric explosion, the energy doesn't disappear. It radiates outward in all directions simultaneously, downward into the Earth as infrasound, upward into the stratosphere as a pressure wave, and laterally, outward at the speed of sound, as a concussive ring that can travel thousands of kilometers before it finally dissipates. The infrasound stations that caught this event, and there were multiple, recorded a pressure signature that had analysts running the numbers twice, because the yield, the explosive energy equivalent of this fireball, came back higher than expected, significantly higher. The energy didn't hit the ground, it spread, outward, upward, and in one direction more than the others, which leads us directly to the anomaly. But here's where it gets strange. Airbursts happen, Chelyabinsk happened, Tunguska happened, we have a playbook for airbursts. This fireball didn't follow the playbook. Every space object that enters our atmosphere follows a predictable arc. Friction, heat, gravity, they work together to pull the object along a trajectory that atmospheric scientists can model with extraordinary precision. Given the entry angle, the velocity, and the composition of the object, you can predict almost exactly where an airburst will occur. The models predicted this fireball would detonate approximately 40 kilometers higher than it actually did. 40 kilometers, that is not a rounding error. For an object to survive that deep into the atmosphere before detonating, it needs to be either denser than predicted, meaning its composition is unusual, or it entered at an angle that gave it more time in the thinner upper atmosphere before the pressure became unsurvivable. The entry angle of this object has been reconstructed from the camera footage, and the angle was not unusual, which means the composition might be. That's not even the part that concerns the researchers most. Let's go back to the color change I mentioned at the start. When a space rock burns through the atmosphere, the colors it produces are essentially a fingerprint. Orange and yellow, silicates, common rock; green, nickel and copper; blue-white, iron; red, nitrogen and oxygen from the air itself heating up. This fireball was predominantly green, then shifted to blue-white. Green to blue-white is a metallic signature. Specifically, it points toward an iron-nickel composition. And iron-nickel objects, metallic asteroids, are structurally far more resistant to atmospheric pressure than stony asteroids. They survive deeper, they stay intact longer, and when they finally let go, they release far more energy in a single burst. This brings us to 1908, Tunguska, Siberia. You probably know the name. A space object, estimated at 50 to 80 meters in diameter, entered the atmosphere over a remote region of Russia and detonated at an altitude of approximately 5 to 10 kilometers. The resulting airburst flattened an estimated 2,000 square kilometers of forest, 80 million trees, gone in seconds. No crater, no surviving fragment large enough to recover, just a flattened horizon stretching farther than the eye could process. And for decades, Tunguska was treated as a freak event, a cosmic anomaly, a once-in-a-millennium occurrence that couldn't be planned for because it couldn't be predicted. Here's what changed. In 2013, the Chelyabinsk meteor struck Russia again, and this time the world had cameras, dashcams, phones, security feeds, and the data from that event rewrote the frequency models entirely. Scientists had been operating under the assumption that events of that size occurred roughly once every 1,000 years. The new models, built from Chelyabinsk data, suggested the real number is closer to once every 100 years, a tenfold increase in estimated frequency, quietly revised, not widely reported. The Tunguska model isn't an outlier anymore. It's a data point in a pattern, and now South America has just added another data point. But hold that thought, because what makes the South America event specifically alarming has nothing to do with the past. It has everything to do with where these objects are coming from right now. Planetary defense researchers, the people whose literal job is to track near-Earth objects and map their trajectories, have been quietly noting a clustering pattern in atmospheric entry events over the last 2 years. The Southern Hemisphere, specifically a corridor running from the upper Pacific coast of South America diagonally across the continent toward the South Atlantic. 3 significant fireball events, all within the last 18 months, all within the same general corridor. Now, before you assume this is being tracked, analyzed, and communicated to the public, let's be honest about something. Planetary defense infrastructure is extraordinarily underfunded relative to the risk it's designed to address. NASA's Planetary Defense Coordination Office operates on a budget that amounts to a rounding error compared to other federal science programs. The International Coordination System, the one designed to alert governments when a significant object is detected, has never been tested against a real-world rapid-onset event. Translation: if something the size of Chelyabinsk entered the atmosphere over a populated region tonight, the official warning time would be measured in minutes, not hours, minutes. The challenge isn't detecting the large objects. Objects over a kilometer in diameter, the civilization-ending class, we track those reasonably well. We know where most of them are. The problem is the middle tier, objects between 20 and 500 meters, big enough to destroy a city, small enough to be nearly invisible until they're already inside our detection window. The South America fireball is now estimated at somewhere between 8 and 15 meters in diameter, below the threshold that most monitoring systems are optimized to catch. And here's the number that keeps atmospheric physicists awake. There are estimated to be over 1 billion objects in the near-Earth environment in that size range. We have tracked fewer than 1% of them. That's not even the part that's spreading. The word spreading in the context of this event refers to something very specific, and it's not metaphorical. When planetary scientists reconstructed the orbital path of the South America fireball, tracing it backward from its entry point, they identified its probable origin region in the inner asteroid belt. That region is currently in a phase that occurs roughly every 11 to 15 years, where gravitational resonance with Jupiter nudges a higher-than-average number of objects into Earth-crossing trajectories. The last time this resonance window peaked at this intensity, 1994, the same year comet Shoemaker-Levy 9 broke apart and bombarded Jupiter with 21 confirmed impacts over 6 days. The events aren't connected, but the mechanism is the same: gravitational resonance, objects being pushed, trajectories shifting, and Earth is in the path of that shifting. The clustering over South America isn't random. It's a geometry problem, and the geometry right now is not in our favor. But here's where it gets stranger still, because the spreading isn't just about more objects. It's about something specific one of those objects is carrying. Spectrographic analysis of a fireball's atmospheric trail is like an autopsy performed at the speed of light. The instruments, ground-based and increasingly satellite-mounted, can analyze the chemical composition of the ionized trail left by a burning object with remarkable precision. They measure the light emitted and decompose it into its elemental signatures. When researchers analyzed the trail left by the South America fireball, they found something in the spectrograph that wasn't expected. Alongside the iron-nickel signature, which we've already established explains the deep penetration, there was a secondary signature, faint, but repeatable across multiple instrument readings: organic compounds. Now, before we go further, I want to be precise here, because this is where the internet tends to sprint ahead of the evidence. Organic compounds in meteoritic material are not new. The Murchison meteorite, recovered in Australia in 1969, contained over 90 different amino acids, the building blocks of proteins, of life. We've known for decades that the chemistry of life is not exclusive to Earth. But here's what makes the South America detection different. The compounds identified in the trail spectrograph include a class of molecules called polycyclic aromatic hydrocarbons, PAHs, which are common in space. And alongside them, a smaller signal, still being analyzed, still debated, a signal consistent with what planetary chemists call prebiotic precursors, molecules that on early Earth are theorized to have contributed to the emergence of cellular life. And here's where the institutional reaction became interesting. The researcher who first flagged the secondary signature, a planetary chemist at a Brazilian federal university, submitted preliminary findings to 2 separate journals. Both requested major revisions before peer review, standard process. But the nature of the requested revisions was unusual. Both reviewers, independently, asked the author to contextualize the detection within known contamination scenarios before the paper could be considered. Translation: prove it's not instrument error before we'll look at it, which, in fairness, is legitimate scientific caution. But here's the thing: the researcher ran the contamination checks, all of them, standard protocol, the signal held. We are living through a moment where multiple streams of evidence are converging on a single, uncomfortable conclusion. Near-Earth objects are more frequent than the models said. The monitoring infrastructure is thinner than the headlines suggest. The objects entering our atmosphere are carrying chemistry we're only beginning to understand. And the pattern, the geographic clustering, the compositional anomalies, the resonance window, none of it has peaked yet. The South America fireball isn't the story, it's the preview. I mentioned at the start that scientists were using a word they almost never use. That word is clustering, not anomaly, not outlier, not isolated event, clustering. In the language of planetary defense research, clustering implies pattern, and pattern implies not certainty, but directionality. Something is moving in a direction, and it's moving toward us. The reconstructed trajectory of the South America fireball, traced forward rather than backward. Following the stream, it likely belongs to, points toward a close approach corridor that becomes geometrically relevant again in approximately 14 months. What's in that corridor? That's the question the next paper will try to answer. That's the paper worth watching for. The rule it broke, surviving 40 kilometers deeper than predicted, means we now have to revise what we assume about the structural integrity of iron-class objects in this size range. Which means our airburst altitude models, the ones we use to calculate safe distances for populated areas, may be systematically optimistic. Not wrong, not useless, optimistic. There's something almost clarifying about watching a fireball cross the sky. For a few seconds, the universe reminds you that the boundary between what's out there and what's down here is thinner than it looks on any map. The South America fireball burned for 11 seconds. 11 seconds to rewrite a model. 11 seconds to open a question that hasn't been asked in decades. And it's not the last one coming. The corridor it came from, researchers have now identified at least 3 other objects in a similar orbital family. Where they're going and when.